Okay, so today I want to start with orthonormal frames, as I promised. Right? So, but my lens a little bit need to start here and here. Okay, I have a boundary here. And then here. Okay, anyway, not that tall. So, orthonormal frames. Orthonormal frames. So I find it a bit peculiar that in many books on differential geometry or even general relativity texts, that this is not discussed often enough. Yeah, I find it quite peculiar because I think it is quite an important topic if you want to interpret your tensorial quantities. Right? So this topic is key to interpreting tensor components. So what am I talking about? So what I'm going to discuss for the first part of the class today is the fact that any metric can be decomposed in the following way. So it's almost like I'm taking the dot product of two vector fields. But this dot product is taking place in this auxiliary space, orthonormal space. So let me just lay out the properties, right? So EA hat I is object with two types of indices. One below, as I write it, this is a coordinate index. So i.e. this is a tensor. A tensor index. So we'll transform. You can also move it up and down using a metric. So move with G or G inverse. And it will transform as we have talked about through Jacobians, with contraction with Jacobians. This is new. So this is an orthonormal frame index. And does not. So it's a scalar, in fact. It's a scalar with respect to coordinate transformations. Okay. And so I'm going to build this up step by step, and then we'll explain how to get here. Okay. So the first thing to recognize is that, well, it's early in the morning and you're going to hear me complain about how I don't like whiteboards yet again, right? I don't like markers and I don't like whiteboards. Let's try to find it. Let's try red, maybe red. So G is real and symmetric. Meaning Gij is equal to Gji. And real because, remember, we're measuring the square of the length between 2 points, right? So obviously length needs to be a real quantity, and therefore the metric itself better be a real quantity. And so these two facts alone tells you, just from matrix algebra, right? So it's a fact that real symmetric matrices can always be diagonalized through an orthonormal transformation. So what it means in particular in this case is that G, if I view it as a matrix, should be expressible as some orthogonal matrix times a bunch of eigenvalues, lambda 1 all the way to lambda p, and then O, which is just the transpose of that guy. Okay. This is a fact from matrix algebra that this always can be done. Okay, so in quantum mechanics, the generalization of this would be that any permission matrix can always be diagonalized through a unitary transformation. The unitary part is critical if you want to preserve probability. So that's something that some of you have probably seen before. So let's use this fact, but now express it in this index notation, because we need to keep track of which indices are the tensorial indices and which indices are the orthonormal ones. And we'll see what it means. So let's go ahead and do it. So Gij, remember, the ith row, jth column of a real symmetric matrix should be expressible as the following, right? So it will be the ith component of the orthogonal matrix contracted with, let me use the A index, lambda A, and then Kronecker AB. So this part is just nothing but this middle matrix over here, consisting on the diagonals of the eigenvalues. Okay, and it's going to be summed over, and then this is O, B, J. Okay, J, OBJ is this guy. So again, I'm just carrying out matrix multiplication using index notation. A summed over A delta AB, and then BJ. So it's a sum over B as well. But this diagonal, so that's why this is a Kronecker delta. And orthogonality, transpose just means that if I rewrite this as O, this will simply become O. So without the matrix, with indices, I don't need to put the hat anymore. But so it's going to become OAI. Okay, this was transpose, but transpose means you swap the rows and the columns, so it becomes OAI, OBJ, and then lambda A, Kronecker AB. Okay, I should say, I know there's 3 repeated indices here. So in case there's some confusion, there's a sum over A. Okay. Otherwise, the rule is that whenever there's a repeated index, when there's a pair of repeated indices, usually we sum over that. But in case it's a bit confusing what 3 repeated indices mean, I still mean it's summed over. Okay, I'm just checking the, I think I'm slightly out of, I better write it over here. Times lambda A, Kronecker A. Now we come to an, yeah, I'll write this again. Now we come to something that I didn't mention earlier, but now it's time to mention, which is that previously I just told you that there are 3 properties about the metric, right? It's real, it's symmetric, and it's invertible, because we want to define the inverse metric. So if it's not invertible, you can't do differential geometry. Right, we'll see. We can't even take the derivative because the Christoffel symbol doesn't exist if you cannot take its inverse. But there is, in fact, another hidden assumption, at least for the curved space that we are looking into. So because we are doing differential geometry of space only, okay? Then all these eigenvalues, I claim, must be restricted to be positive. All of them are positive. Okay? So I'm just going to put curly bracket. When I put curly bracket, I just mean the set of all the eigenvalues. So lambda 1 through lambda d, they're all positive. It's an assumption. Okay? It's an assumption because we're working in space. If you do special relativity, for example, then you will start to care about the differential geometry in space-time. And what you would then do is that when it comes to the time part of the metric, you will need to make a choice. Either it will come, so just as an aside, and I can write it here, it doesn't have to appear in the video. So this is an aside. Okay. If you work with space-time, in space-time, we can still define something analogous to the square of the distance. Okay, but it would turn out to be, either be, actually, let me do flat. Okay, just for simplicity, it will turn out to be either dt squared minus dx dot dx, or minus dt squared plus dx dot dx. Okay, and so if you write this as a matrix, is either 1 minus 1 minus 1 minus 1, we live in 1 time and 3 space dimensions, or minus 1 and then plus 1 plus 1 plus 1. So you have to make a choice. Either is 1 versus minus 1 or minus 1 versus 1. There needs to be, is a very important fact, that time and space, they are unified in this differential geometric language of space-time. But time and space are different. Okay, they are different. And so this assumption is no longer true. Like one of them is the opposite sign from the others once you start to do space-time. But for what we are doing, we will make this assumption that all the eigenvalues are positive. And once we make that assumption, that means that we can take the positive square root of these eigenvalues. Okay. You learn some complex calculus now, so you know if you take the square root, there's always two solutions, right? And so you've got to be careful what you do. So if we do that, then at this point I can write my manipulations in the following way. I have O, A, I, and then I'm going to stick in a square root lambda A and package it together like that. And then OBJ, square root lambda B, just to make it look symmetric. And then connector AB. I've not done anything different, right? It's still the same object over here. It's just that I've made use of this assumption that lambda is positive. So therefore I can take its positive square root. And so what you see is that when I multiply these two guys together, because A equals to B anyway, this guy, the product of these guys, is actually equal to by lambda A. Okay? But now I can package this guy together and call this what I wanted to say, what I was writing down before, which is epsilon A hat I, and this is epsilon b hat j. And now I arrive at what I have already claimed previously. So connector AB, and an epsilon a hat I, and an epsilon b hat j. Okay. So what you notice is that actually when I write this way, it should be clear that I'm just basically trying to group things together and writing it as a sum of squares. So in fact, let me do that from the perspective of the square of length, and see how that looks like. Because that will help you in many simple situations. It will help you read off what these orthonormal fields are. Just the mechanics of it. And then, like I said, I want to discuss a little bit why there are two sets of indices, and in particular, how do they transform? I want to emphasize that point. Much of tensor calculus is about how do things transform, because that will determine whether or not they make sense in arbitrary coordinate systems. So, remember that dl squared, the square of the length between x and x plus dx is the contraction of these components with dxi, dxj. Right? These guys are the actual displacements. And when upon contraction, they form a square of the length. And now, in this new language, what do we have? We have epsilon a hat I dxi, and then epsilon b hat j dxj, and then connector AB. Okay. I think it still can be seen. And then with this packaging, should be clear what is going on here. So if I call this epsilon a hat and this epsilon b hat, then it should be clear that all that is happening is that I now have a sum of squares. So we have epsilon a hat squared, right? This is epsilon a. But this is epsilon b hat, but then you're summing it over, contracting it with the connector delta. So A equals to B, and you're just summing it from 1 to D. I.e., this is some sort of generalized Pythagoras theorem. I should put theorem in quotations, right? It's just a repackaging of the metric. So it's not really a theorem, right? It's not. Theorem means you start from somewhere and you go through, many steps of logic, and then you come up with a new result, right? But I'm just repackaging the metric in this way. But this repackaging should make it clear that you can always repackage the metric as a sum of squares. Okay, and so for example, let's look at the simplest example in Cartesian coordinates and in flat space. So right away, you see it's already the sum of squares. Okay, so that means that means that I can view epsilon 1 hat as basically, remember, epsilon a hat is the contraction of the orthonormal frame with the d-axis. So this is actually epsilon 1 hat I dxi. But if you pick this guy as your first guy, then this is only just epsilon 1 hat x dx. Okay? And in fact, that means that epsilon 1 hat I is 1 when I equals to x, and 0 when I is not equals to x, when it's equals to y and z. Yeah? Likewise, well, I'm just writing it out very systematically, but you can basically just read it off. You can tell right away what is going on. For example, epsilon 2 I is therefore Kronecker I y, and then epsilon 3 hat I is therefore Kronecker I z, and that is just another way of saying this guy. Okay? That's a bit too simple. So let's do the spherical coordinate example. Okay. So for example, so that's example 1. Example 1. Example 2. Let's say we instead still in three-dimensional space, but now let's switch to spherical coordinates. And so we've already seen that this gives you dr squared plus r squared d theta squared plus r squared sine theta squared d phi squared. Okay, and so again. Is already a sum of squares. Okay? So I can identify this with epsilon 1 squared, this guy with epsilon 2 squared, and this one with epsilon 3 squared. Okay? I can call it epsilon r if you want, r hat, and epsilon theta hat, and epsilon phi hat. If you want, right? It's a choice of notation. But I just want to enumerate them, so I'm just going to call them 1, 2, 3. But now, again, you can see that epsilon 1 hat I, dxi, must be just dr. Okay? Which means that the only component that you need to sum over is dr. And in fact, in this case, epsilon 1 hat I is again just 1 when I equals to r and 0 otherwise. Okay, so and then epsilon 2 hat I, the xi, again only involves theta. So but now the something slightly non-trivial, right? Is r squared d theta squared. R d theta. Okay, and so something is non-trivial here because there's now an r here. So epsilon 2 hat I is Kronecker I theta times r. Okay, if you write it in index notation. Okay. Again, when I is only when I equals to theta, when it's non-zero. When I is equals to r and phi, it is 0. And the last thing is epsilon 3 hat dxi is r squared, r sine theta phi. Okay? And therefore, epsilon 3 hat I is Kronecker phi I r sine theta. So, for simple diagonal metrics, like the ones that we are dealing with, you discover it's actually very simple to rid off the orthonormal frame fields. Yeah, very, very simple actually. It becomes a little bit more complicated when you have off-diagonal metrics. And in fact, I will give you an example to work on in your homework. I think not yet, yeah, maybe next homework. When is homework due? Next week, is that right? Next week?
Next Friday.
Next Friday, okay. So remember, one more week. So I really recommend that you start your homework early. I think this homework is considered fairly light already. Because I gave you, I think, 12 problems or something like that. There will be more. Okay, I think I gave too few problems this time. So, but anyway, I recommend, highly recommend that you start early. Otherwise, you'll have trouble if you try to do it at the last minute. You're going to run into a lot of trouble. And homework, as you may recall, takes up the bulk of the grades in this course, right? I like to reward hard work, consistent hard work. Right? If you just do well on the exam, sure, you should get high grades, but so should you work hard for the rest of the semester. So I actually prefer to put the weight in the homework. And then within the week, next week or so, I'm going to put out the first presentation problems, and you guys should look over it, find some friends, form your group. I'll say more about it next week, but you should find your friends, maybe, I think we have like 9 people. How many? 9 people, yeah. So probably 3 to 1 group. So make some friends, and we'll have 3 in each group presenting 1 problem, right? I'll give you probably maybe 4 problems to choose 3 from, and then you guys can come up here and tell us how you solved it. Anyway, I'll say more next week. I'll try to put it out over the next week or so, the problems. Okay, so the remaining thing is conceptual, which is that we have recognized, basically through diagonalization, that I can write my metric in this form. But what I haven't discussed in great detail is how do these guys transform? I said it, but we need to understand a little bit how it goes. So let's start with the coordinate indices, the tensor indices. Right? So the tensor indices are, of course, the x and the y, I and the j's. Right? And so this is easy to understand enough because, for example, if I contract these guys, it's still the full metric, right? This is after all equal to this. So if I do a coordinate transformation, it has to give me GAB, or I better give, let's call it M and N. Then it better give me G of M prime and prime of C. Okay. And that means what? That means these guys must be contracted with these guys. So let's see. So it's Kronecker AD, and then epsilon A hat I of X of C. Remember, these guys, all of these guys should depend on space, because this is just a bunch of constants. And so if I package this guy together with this factor of the orthonormal frame field, then I see that I can read off this transformation property. Namely, this guy better transform like a 1 form. In the lower index is a 1 form. And this guy, epsilon B hat J, will be contracted with this other Jacobian dx J, dCB, and like I said, these indices are tensor indices. Because that's how you get in the new G n prime n prime coordinate system, you will still have the Kronecker AB. Remember, we got to this form in using a very general argument. So it has to be true in any coordinate system. It's just that these guys will accordingly take different expressions. So it will be epsilon A hat, and then this will be now M prime, and now my orthonormal frame field will be in the C coordinate system, and this will be epsilon B hat N prime C. Okay. Meaning this is equal to, let's not put so many equal signs, but this guy. Okay, thank you. So, yeah, I always forget, this camera seems to be restarted every half an hour. Okay, so good. So, now let's consider this, taking this object and doing what with it? I'm going to take a epsilon a hat I, and I'm going to replace it with this, basically this matrix applied to it. So it will be A, and then say epsilon S hat I. Okay, I'm going to literally replace it with this guy. So now the right hand side of this relationship will become what? It will become, let me write it down first, R L delta AB, epsilon A hat I, epsilon B hat J is going to be replaced with connector AB, and then remember, I'm going to multiply this guy by R hat, and this guy also by another R hat. So what's going to happen is I'm going to have R A, let's call it L, and then R hat B, M, L, N, because N is over there, so let me do S, right, L, S. And then this guy is contracted with epsilon L hat I, epsilon S hat J. Okay, again, these two guys came from replacing this guy, and these two guys came from replacing this guy. And I'm packaging it this way because the tangent vectors in two-dimensional flat space, but I'm going to do it in polar coordinates. So 2D flat, but in polar coordinates. R and phi. So that means that you have V of R, dr, plus V of phi, d phi. Right? That's what a tangent vector is. It's a directional derivative. There is a slight problem. It's a directional derivative for sure, meaning you can think of this as dr d lambda, and this is d phi d lambda. But if you want to identify, if you notice that V R is not equals to V phi in dimensions. So interpretation is not easy. Physical interpretation in particular. Physical interpretation is not easy. So the first thing we should do is at least get it to the same dimensions. And furthermore, they are not, so furthermore, we want to, in this case, we want to make sure that we can actually interpret it as a velocity. Right? So it's a directional derivative, but the additional layer of physical interpretation as velocity is unclear. So maybe for VR, so VR is dr dt. Maybe that's okay. But V phi is d phi dt. But that's not length over time. Okay. So what you will notice is that these two problems are related. That the dimension, inconsistency of the dimension not being length over time is in fact related to the fact that we cannot interpret this in a straightforward way. So what we want to do is we want to first convert this from a partial derivative basis, which is the coordinate basis, into so let's proposal. Convert V into orthonormal basis. Let's try to do that, and then we'll see that quite naturally, at least in this case, there will be a natural interpretation that emerges that allows us to now interpret the orthonormal V5 version. So V, in fact, nothing but the velocity in the phi direction. Okay, so VR is probably okay, but let's see what happens for V5. So let's go ahead and do it. So the point is the following, right? So let's go kind of back up a little bit and see how do you do this in general. And it's most easy to do it in the level of index notation, so I'm going to do that. So what do I mean? So Vi is a tensor, is a coordinate. It's a coordinate vector. But if I contract Vi with epsilon, say a hat I, now this guy becomes a coordinate scalar. Why? Because remember, this pattern index transforms as local rotations. I'm allowed to replace this guy with a rotated version of it, and it's okay. The same amount of information is still retained within the metric itself. The interpretation is another matter. What does it mean to rotate this? What does it mean for this quantity? Right? But let's take things one step at a time. But because this is a coordinate index, and that's a coordinate index, we see that, we have seen it before, that whenever we take the contraction of one up and one down index, this guy, the transformation of this guy will cancel out the transformation of this guy. So, for example, if this is an x coordinate system, I can immediately write down that this will be V j prime in the c coordinate system, epsilon a hat j prime in the c coordinate system. I don't have to think, because I know right away that this is a scalar, and I can do that right away. But the point is the following, there's now a way to go back and forth. It's not like I threw away something when I contracted it with these orthogonal frames. After all, you can just count how many components I have. I runs from 1 to D, so I have D components. Well, A runs from 1 to D as well. Okay? So if you view this as a matrix, I still have a D by D matrix. It's just that this matrix came from taking the square root, roughly speaking, the square root of my metric. Right? This is the square root of the metric. And so, but as far as A is concerned, it has the same number of components as I. So, as I want to show you first, there is no loss of information when you contract your V with an orthogonal frame field. And in fact, we can go back and forth. So if I give you this, in fact, I'm going to define this object to be V a hat. Okay? And the a hat, again, is inherited from the a hat over here. So again, my claim is that Vi and V a hat contains the same amount of information. What does it mean? It means that if I give you Vi, I can give you Va hat, which I have actually just done. And now I'm going to show you if I have give you Va hat, how do I go back? Well, actually it's simple enough. So all you have to do is Vi is in fact given by VA hat. And then you have to contract with EA hat I. What is this object? Well, this object is not this object. EA hat I with this placement of index is, remember, A hat actually is contracted with a Kronecker delta. So basically you can move A hat, the header index, in any way you want. So this is A hat upstairs. But this guy is a coordinate index, so we have to be careful then. So this is actually J, and as we always do, you move the coordinate index by contracting it with the inverse metric, in this case from down to up. Okay. And that's how you do it. But how does this come about? Okay, so this is good to have a few words about this. So essentially, what we do is, we should remember, is that we have managed to diagonalize the metric in one way. So we give you the metric, and I can write down its orthonormal decomposition. It turns out that we can go the other way around. So it turns out that I can now ask, what's the contraction of these two indices? So let's do that. Gij epsilon A hat I epsilon B hat J. And turns out, so the proof is not difficult, but it's just a little bit technical, and I'm just going to skip it, right? You can find it in my notes, actually, but I'm going to skip it. But this turns out to be Kronecker AB. So if you think of these guys as vectors of one form, basically this is epsilon A hat. If I raise this index, it will be I, and then this will be epsilon B hat J. Okay. It's like basically, oops, I'm sorry, I. This is basically like taking the eighth. This is, if I view A and B as the label, so it's the first orthonormal frame, or the second orthonormal frame, or the third, and so on. Then I'm just taking the dot product in curved space. This is the dot product. In curved space between the A and the B orthonormal frame field. Orthonormal frame field. Okay. And if you believe my assertion, as I said, the proof can be found in my notes. Starting from this guy, we can prove the kind of the inverse relationship that that this is true. And basically, it tells you that what it's telling you is it justifies the orthonormal part of this claim, and that's why it's important that I say it. Why is it so? Because when A equals to B, the right-hand side is 1. That means that the dot product of the eighth vector field, orthonormal field, with itself is 1. If I dot it with somebody else, when A is not equal to B, and I dot it with someone else, then the answer is 0, which means it's perpendicular. So I really do have a set of orthonormal fields. But this is the very important part I want to emphasize. So that's essentially what I'm doing. When I'm changing my vector field from a coordinate basis, these i's are contracted with a partial derivatives. Now, if I contract it with the orthonormal frame fields, these guys, there's a reason why I put a hat on it. Remember, in vector calculus, we put a hat on things that are unit length. So that, in fact, this notation, in fact, reminds us that if the index of my vector what used to be a vector, is now hatted. I've actually now expressed it in an orthonormal basis. So let's in fact see how that works out in practice. Okay, so for example, let's return to this problem and see what is r hat, v r hat, and v phi hat. Okay. So yeah, let's do that. Cool. Now I don't need this part, so let me start here. Okay, so we're in polar coordinates, so 2D polar coordinates looks like the following, right? dr squared equals to dr squared plus r squared d phi squared. Okay. So you can read off. Now I would prefer to call my epsilon r hat I, and I'm just going to read it off. The only component in the square involves dr. So the I component only involves r, and because the coefficient is 1, it's just connected over. And likewise, epsilon phi hat, which refers to the square of this quantity here, right? So I'm okay to call it phi hat. If my orthonormal thing involves the superposition of dr and d phi and d theta and whatever, then calling it r or calling it phi or theta would not make much sense. Then I would just have to enumerate it with 1 or 2 or 3 or whatever, or some other symbol. But because there is in fact a one-to-one relationship, so this refers to this, and this refers to that, and this I is now R connector I phi. Yeah? And so now we're now we're ready to ask, for example, what is VR hat? Well, VR hat is VI epsilon R hat I. Remember, you always contract to make sense, right? For this thing to make sense, it's now a coordinate scalar, and it's a coordinate scalar, it means that you're contracting the coordinate indices together, and this becomes VR, actually let's write down in steps, VI connector RI times 1, which means VR hat is in fact VR. Okay? So the interpretation is that the velocity, the actual velocity, is the same as the coordinate component, the component in the coordinate basis, at least for the r direction. But now let's look at V phi hat. V phi hat is V I epsilon phi hat I. Okay, and this is now Vi, and then now this is the important part. We have R times connector I phi. Okay, which means that there is a difference between V phi and V phi hat. It differs by a factor of R. Okay, this is a demonstration of why this is useful, because now, what is it? V phi hat. Remember, V phi, the coordinate basis, we can always interpret it as a directional derivative, meaning it's the derivative of the particular coordinate you're studying with respect to time. It doesn't always have to be a real time, but in this case I'm going to say it is real time. But otherwise you can always interpret it as derivative with respect to some fictitious time, or some lambda, some arbitrary one-dimensional coordinate. But in this case, it is useful to think of it as a real time, because now my V phi is this guy, but I'm now multiplying it by R. Okay? What is R d phi? This is just geometry. Okay? So you got at the origin, and this is R. Remember, d phi is just a little angle that you sweep out. And so if you sweep out this angle, the tangential velocity right? So VR hat is the component of velocity in the radial direction. It can also be inward pointing, but I'm just going to say it's outward pointing for the moment. But the tangential component is exactly r times d phi divided by t. So this is, in fact, now the tangential velocity. Or let me put it, because tangent, now in differential geometry, we call it tangent vector. Right? So let me use a different set of words. This is the velocity component in the phi direction. Okay? As the geometry shows you. So again, just by going into an orthonormal basis, I have managed to, at least in this example, converted what was interpretationally a little bit ambiguous. What is d phi dt? That's not speed. That's not a velocity, right? It's not length over time. It's angle over time. Angle is dimensionless, right? So d phi dt is just 1 over time. But now, when once you go into an orthonormal frame, you have r d phi, which, if you just think about the geometry a little bit, immediately allows you to interpret it as an actual physical velocity, in this case, in the phi direction. Okay? So I claim, right? So I'm not proving it. It's not a math problem. Mathematicians would probably not like how I present it, but it's not a proof. In any case, mathematicians very often don't care about physical interpretation. Right? They care about the rigor of their arguments, but very often they don't care about the physical interpretation. Sometimes they do, but not. Very often they don't. But in this case, I think it's very important, particularly for physics, to understand that this is one purpose, one key purpose of using and understanding the orthonormal basis. So my claim is that there is a whole problem. I have to check. So let me just write it down first. The claim that to interpret the next claim is an informal problem. This claim is just my assertion. Interpretation. So to interpret the components of a tensor, express it in an orthonormal basis. That's my physical assertion. The claim number two, claim number one. Claim number two, to check the consistency of the claim number one, claim number two is homework. You can show that if you express your tensor in an orthonormal frame, all the indices are now tethered. All of them have the same dimensions. Physical dimensions. Okay, so let me just start you off with that, and then I'll come back to this later, because I need to add a few more technical explanations to what this means. The first thing to realize that if I write down a tensor as a superposition of its bases, so whatever this is, right, I1 through IM, and then J1 through Jn, well, you already know what this means. This is a superposition over the partial derivatives, if you like, a coordinate basis. If this sum makes sense as a physics object or a geometric object, it better be that the entire sum has consistent dimensions. it doesn't quite make sense to add length to currency. You know, $1 plus 1 meter. You know, what does that mean? I don't know. You tell me what that means. So it has to have consistent dimensions if you're dealing with something meaningful. Okay? Of course, you can just insist on doing it, but it's not meaningful. But if it means something, that means that this guy, term by term, this guy has one consistent unit, consistent physical dimension. Okay? And what I'm going to tell you about claim 1, I'm going to fill in some more technical details, is going to allow you to prove claim 2, which is, I believe, a homework problem. So I'm going to, again, probably going to end up doing a little bit of your homework, which should get you a little bit angry. Right? Did I tell you guys this? You should get a bit angry. Have I told the students this? If I do your homework for you in class, you should become very angry.
At this moment, I gradually use something very
You would prefer to be angry, is that right? You want to become, you're not angry enough. You want to become more angry. Okay, I'll try my best. Okay. Okay. Anyway, so let's come back to claim 1. But like I said, they're related to each other, intimately related to each other. Okay? Because it's only because it's part of why you can interpret things properly is because they have the same dimension. Otherwise, you know, if just by changing your directions, you get from length to mass, or length to angles, or whatever, then how the heck can I make sense of what this entire object even means? Okay, and so that's one of the claims that I'm making. So, but anyway, so let's come back to what it means to express a tensor in an orthonormal basis. So usually we have now gotten used to the fact that a vector, for example, is a superposition over partial derivatives. And what is going on is that now we have also shown that VI can be written as VA hat superposed over the orthonormal, first contracted with the orthonormal plane fields, but with this index lowered and this index raised. So I claim that this guy can now be packaged together, and now I can call this VA hat epsilon A hat. Okay, so again, epsilon A hat is now epsilon A hat I, and then contracted with the partial derivatives in your particular orthonormal, particular coordinate system. Remember, previously we introduced something. We call it epsilon A hat, and with the upstairs. So this is a little bit tricky, and I need to emphasize it. With the extra index in place, say this, okay? With the coordinate index present, this guy is the same as A hat upstairs I. The coordinate index needs to be moved with the metric or the inverse metric. But A hat can be moved up and down, at least when you're dealing with flat space. At least when you're dealing with space. Okay? If you're dealing with space-time, that's a different matter. But this is true in closed space. And let me underline space. It's not true in space-time, but in this course, we're only going to deal with space, right? Because I have other things to do. We need to talk about. I'm supposed to talk a bit about group theory, about integral transforms, and then along the way, I'll show you some special functions and so on. So that's more things to do. But without the index, then we need to make a careful distinction. Epsilon A hat with the index downstairs means this. Whereas epsilon A hat with its index upstairs means epsilon A hat I dxi. And remember where this showed up. This showed up when we expressed the metric as kind of a generalized Pythagoras theorem, which now I write as epsilon delta AB epsilon A hat epsilon B hat. Okay. So that's where this guy comes up. But now you see where this guy will show up. This guy shows up if I want to repackage my basis partial derivative into a new form, and I claim that this guy in this form is orthonormal. Okay? So let's see. So remember that previously we were able to define the dot product between partial derivatives. Right? These are basis vectors. And the basis vectors, remember, in linear algebra, we need to have some notion of an inner product. And so this is a definition in differential geometry. If you have partial derivatives, the purpose of the method is to give some meaning to what it means to take the dot product between the partial derivatives. One of the meanings is to take length, to study distances. The other one is to, in fact, study the dot product between, it gives you a geometric meaning to the dot product of partial derivatives. Partial xi delta into partial xj is the metric. Okay? So we can use this to work out so that's the vector. Let's do it for the one form. Let's say AI dxi. This is the one form. And this is usually how we express A as a superposition over the infinitesimal displacement. But now, let's remember that AI can be replaced with its orthonormal counterpart. So let's call it B hat, because this is capital A, so I don't want to put too many A's. So A, B hat. But now I'm obliged to contract it with B hat, epsilon B hat, and then I. Okay, so this guy here is AI, and then dxi. But now let's package this guy together, A B hat, and then epsilon B hat I dxi. So this guy here is what we just encountered, what I just reminded you again, showed up is the fundamental object that shows up in the metric as kind of a generalized Pythagoras theorem. The square of this guy. So this is in fact nothing but A B hat epsilon B hat. So the epsilon A hat downstairs are the orthonormal basis vectors, whereas these guys, when viewed in this way, are now the orthonormal basis one forms. Okay, and if you don't believe me, we can take a quick calculation. A hat, B hat. And let's calculate what this is. This is epsilon A hat I, epsilon B hat J, contracted with dxi. So this guy and this guy is epsilon A hat. This guy and dxj, this guy and this guy is epsilon B hat. But this guy, by definition, is gij upstairs. And then epsilon A hat I epsilon b hat j. And as I said, this is the same. This guy is exactly the same as this calculation, which in turn is connector AB. So, as I claimed, these guys are the orthonormal basis one forms, and those guys are the orthonormal basis vectors. And so what is key in your proof to understanding the claim number 2, that all tensor components, when you write them in an orthonormal frame, you would discover all of them have consistent dimensions. The first thing to write down is to understand what are the dimensions of this guy and what are the dimensions of this guy. That's the key. That is the key. Yeah. Once you understand that, then any tensor can be expandable in terms of this basis together with this basis. Right? Actually, let me just make sure that is clear. So instead of writing down Ti1 through Im, J1 to Jn, contracted with the partial derivatives, I1, dx, I1, dx, J1, all the way to dx, Jm. Instead of using a coordinate basis, you can always write it in terms of an orthonormal basis, which now you know how to do. A hat 1 all the way to A hat m, B hat 1 all the way to B hat m is now going to be contracted with epsilon A hat 1 through epsilon A hat m, and then this will be epsilon B hat 1 all the way to epsilon B hat m. And so hopefully now we can see why it's important to figure out first what are the dimensions of these epsilons. Because once you figure these guys out, then you can figure out what this is. You can write it down explicitly in terms of the physical dimension of the tensor itself. Remember, the tensor itself is a superposition over a bunch of terms. And for it to make sense, every term must have one consistent unit, right? And so once you figure it out, once you're given what that is, and once you understand what are the units of these guys, then you know what these guys are. These guys are inconsistent dimensions, but these guys are consistent dimensions. All of them are the same dimensions. I mean, yeah. There I go again. I've done your homework.
Thank you.
Yeah. I can only shake that. You should get very angry. 应该很生气。
But when we have completely no clue how it should be done, it's a different story.
Okay, any questions for me? So I know all this stuff is very new, right? So you should feel free to ask questions. Anything that's not clear, you should definitely ask. But anyway, I'm around. So far, only this guy has come to look for me. Right? I don't see anyone else. It's like there's only one person in the class. So please feel free to come by and love me. Okay? Because I don't bite. I'm here to help, but it is your duty. You're here in school. It's your duty to make the effort to seek out the resources you need to make sure that you understand all this stuff. Right? I can only do my part. You have to do your part. Okay. So let's see. I am almost out of time. Just give me another 10 minutes. Let's see where we are. think we are ready to talk about, I think we're ready to talk about derivatives. So we have talked about dot products, we have talked about angles, we have talked about volumes, orthonormal frames, but we have not talked about derivatives. So I think it's time to talk about derivatives. And then we'll take, of course, actually maybe I'll start talking about integrals first. Because this actually, the one form is in fact, the starting point of an integration procedure. Right? So maybe I'll start there, and then we should talk about derivatives finally, right? Because so there is quite a bit of machinery, but let me just remind you, when you start out learning quantum mechanics, it's a little bit like that as well. Right? So you really understand quantum mechanics. You can spend a whole semester kind of waving your hands and talking about waves and stuff like that. But ultimately, the underlying framework is linear algebra. You need to know what a vector space is. You need to know what linear operators are, and so on, to be able to speak the quantum language. Right? The quantum language is linear algebra. So likewise, calculus, particularly if you want to do multi-variable calculus, if you want to do it in a consistent way. By consistent, I mean you need to be able to do it in any coordinate system. Even if you are not interested in general relativity, I claim you need to know differential geometry. So why is this one form related to integration? So remember, in vector calculus, we call it a line integral. And what do? We say, oh well, we have a V, we have a vector field, and then we also have a path. We have a path in space, x of lambda, path in space. And we want to say, okay, let's take the line integral along a V along this. So we do this, right? So we take this path, and then we say V dot dl. All of this, I claim, of course, is correct, but all of this implicitly assumes that you are working with Cartesian coordinates. They don't quite tell you that, but whenever you write something like that, the dot product itself implicitly assumes you are working in a Cartesian basis. But so what is the correct way? What's the more, I don't want to say this incorrect, it's correct as it's being taught. But what is the more general way to talk about line integrals like that? In fact, it is the one form. Okay? So the reason why you want to do this is because this gives you a number. Okay? And this number, in particular, should be independent of whatever coordinate system you use. Okay? So you'll hear me say this again and again. You should, whatever you compute, that is of physical relevance or geometrical relevance. If you're measuring an angle or a length or you're actually measuring some mass or something that can be measured, that will be invariant under coordinate transformations. So you cannot, the answer cannot possibly depend on whether you're using Cartesian coordinates or some funny hyperbolic coordinates or whatever. Right? It cannot be. So this is why this is the invariant way. The AX dxi is coordinate invariant. Because I did not make any assumption about what coordinates I'm using. And I know how to transform from one coordinate system to the other. In particular, if this is the x coordinate system, in the y coordinate system, it will be simply aj prime dyj. Okay? If you don't like, you put an I, and it's just a domain index. Okay? So if this is a of x, this will be a of y. And I know it's coordinate invariant because as long as this is these guys transform accordingly. Okay? Whereas this guy looks is completely correct if you mean it in a Cartesian coordinate system. But now, if you ask me, okay, what if I go to some funny coordinate system? Then you're going to start thinking, oh, okay, you are going to first start in Cartesian, and then I'm going to relate the Cartesian to some other coordinate system, and then if it gets increasingly complicated, then you get stuck at some point. Okay? Or at least you're going to think very hard. But if you know your tensor calculus, you don't even have to think. You just write down what your one form is in whatever coordinate system you want. You don't like that coordinate system, you change it. How do you change it? It's just watching the coordinates. Okay? So the line integral, the coordinate invariant way of defining a line integral is in fact to integrate one form along some path. Of course, to actually carry out the integral, you want to convert it into a one-dimensional integral. So this will become, for example, if you want to integrate from here, lambda 0 to say lambda 1. Right? So that x of lambda 0 is the initial point, and x of lambda 1 is the final point. So to integrate from n to n, you just take the integral from, you convert this to a one-dimensional integral over lambda, and this will become ai x of lambda, meaning now you have to evaluate your tensor component, your one-form component, along the path, and then this will be dxi d lambda d lambda. Okay? So I have to assume that you know what a trajectory is, and therefore I can calculate its tangent vector, and by taking its derivative, and that's the thing that you can carry out. Right? But like I said, it works in any coordinate system you want. If I don't like my x coordinate system, I can certainly just do it in some other coordinate system. So for example, I can do it in y if I like. dyj, d lambda, d lambda. And there's a well-defined description of how we go between the x system and the y system, right? Because you know that AJI prime is just related to the x basis to the Jacobian. So it's very well defined. You can always go from coordinate system to coordinate system, and you are guaranteed you get the same answer no matter what. Okay. So that is integration, line integration. And I'm almost out of time. So next time, I'll just advertise, next time we will start taking derivatives. This is an example of an integration. Later on, we'll try to improve on this by looking at volume integrals. There's a reason why we call it a form. But at the level of the one index guy, there's not much to it except what I just told you. But then when you have more integration variables, then there starts to have a meaning to why we call it a form. It has additional properties that we should study a bit more carefully than what we've done so far. But the next thing we want to do first is to study how to take derivatives. How to take derivatives. Again, in arbitrary coordinate systems. And what that means is, of course, when you take a derivative, you want to make sure that what the output is a tensor. And I claim that if you just take a partial derivative, you take the tensor components, take the partial derivative of it, that is not a tensor in general. Sometimes in Cartesian flat space, sometimes it is. But in general, no. The answer is that it is not. So why that is the case, why that is not a tensor, and how to fix it, we will talk about it next time. Yes, we're going to start. We're going to start seeing new objects like the Christoffel symbol and so forth. And that will be built out with a metric. Any questions for me? Okay, so again, one more week to your first homework due date. So please come and look for me if you have any problems. It's good for you guys to work together, right? So my only requirement is that you need to turn in an honest piece of work. Make sure that you write down your solution. Right? After all, you are the one trying to learn it. But of course, it is okay to work together, right? And so you can learn from each other. So please start soon because my homework is a little long. All right, see you guys on Wednesday.
要吃饭吗？你要吃饭？
应该不会。
好，
我要去家附近的咖啡厅。
不用跑电视，还没。
要，可是我